All right, we're gonna go over our fourth section in Unit 12. We're still in probability. This section involves something called compound probability. So the previous lesson, just talked about single events going on, one thing going on. Compound probability, as you can read, is one event made up of two or more smaller events going on. If the occurrence of an event does not affect the other event, they're called independent. So one does not affect the other. If the occurrence of one event does in fact affect another event that's occurring, it's called a dependent. One of the things I'm going to have you guys do is be able to read a passage and say, yeah, these two things going on are independent of one another. They don't affect one another. Or, yeah, what happened here at the beginning is now affecting what's happening second or third. We've not used this much in class because of the way everything's been going on with COVID. But it's like, can you name a situation in our class where we use compound probability, particularly dependent probability? And the answer to that question is the bingo ball machine. All right, so basically how it works is, as I spin the ball, I call on a desk number. Every desk in here has a number. That ball comes out of the bingo ball machine. What it is doing is it is affecting the denominator, okay? It's changing what we call the total frequency. And so, yeah, as you remove balls and do not put them back, it's the next roll is dependent on what happened before. This next slide will kind of go through some of the, let's roll this out here. It'll go through some of the problems talking about independent and dependent. All right, so here's just a few. We're going to try to answer these to the best of our ability based on stuff we've done in class or you may have done in life. It says, are the outcomes of each trial independent or dependent? So we're just going to put an I for independent or a D for dependent. So I roll a die, then spin a spinner. So the question is, does rolling a die affect how a spinner lands? And no, these are independent of one another. So these, we're going to put I for independent. Pick a card from a deck of cards. Do not put the card back. Pull another card. Did our frequency change when we did not put the card back in the deck? And the answer is yes. We went from 52 cards down to 51 cards, and that increased our chances of trying to get a desired outcome. So this was dependent upon this. Roll a cube, then flip a coin. Do they affect one another? No, they do not. They're independent of each other. You eat an M&M from a bag and then eat another M&M from the same bag. Did eating the second M&M, was it affected when the first M&M was removed? And the answer is yes. If you were trying to pull a specific color out of the M&M bag, if you eat one of the M&Ms, you're changing that denominator in your probability fraction. So it does affect the outcome of the second pull. So these are dependent on one another. And this last one is always open for debate. Picking your nose, then scratching your butt. Are they independent or dependent of one another? Some may say it's dependent, but hopefully one doesn't affect the other. And we would call these independent events, independent occurrences. All right, moving right along. So it says, let's do the math here. So it says, a desk drawer contains 5 red pens, 6 blue pens, 3 black pens, 24 silver paper clips, and 16 white paper clips. So we have 2 categories. We have pens and we have paper clips. All right. It says, if you select a paper clip and a pen from the group without looking into the drawer, what's the probability of pulling a blue pen and a white paper clip? So what we do here is, well, first of all, we need to count up how many pens we have. In the pen category, it looks like we have 5, 6, we have what, 14 pens, right? And then how many of them are blue? Well, we have 6. So just pulling a blue pin, we have a 6 in 14 chance. What about the paper clips? How many paper clips do we have? Well, with the paper clips, it looks like we have 40 paper clips total. How many of them are white paper clips? Well, we have 16 of them. Okay? So the $1 million question is, what do we do with these two fractions, right? We know how to do the probabilities of each individual one, but we've never been taught, what do we do when we're trying to do two things at once, right? So literally, you're doing this. You're reaching down into the drawer, you're not looking, you're trying to pull out a white paper clip and a blue pen. This is called compound probability. These are independent of one another, but they're still compound. So what do we do with these fractions? Do we add them, subtract them, multiply them, divide them? The answer to that question is that we're going to multiply those independent probabilities together, okay? We have to multiply them together. So we're going to grab our calculator, and this is what I like to do. I just kind of like to set it up as my fractions. So we'll do alpha y equals, all right, 6 over 14. I'm going to times it by 16 over 40. And the reason, hold up. The reason I'm doing this is because what it does, if I put this into the calculator, it actually simplifies my fraction for me, which is pretty nice. 16 over 40. So you don't have to worry about simplifying the fraction. Okay? Check it out. So you have a 6 in 35 chance of pulling a blue pen and a white paper clip. So when we've talked about this, right, Mr. Mann likes them in percentages. We said it's 6 over 35. And as a percentage, okay, so we're going to pull it back up here. Make sure you can see the screen. We're going to do 6 divided by 35. And so your decimal place would land right here. So we call it 17.1%. 17.1%. There you go. Okay? Says you roll a die with your right hand, okay, and you flip a coin with your other right hand. Hopefully that would be your left hand. What is the probability that your coin would land on heads and that the die you roll would land on an even number? So let's do the coin first. So with a coin, you have a 1 in 2 chance, theoretically, of landing on heads. And then we're going to multiply to that the die roll. The die roll, even numbers, is 3 out of 6. Hopefully you won't need your calculator to do this math here. I don't know, some of you might. That would be 3 over 12. And 3 over 12 is a reducible fraction of 1/4. And hopefully you know that 1/4 is a 25%. Okay? So as we're going through these compound probabilities, the word and I need to specify this, and I'm saying it right now in this video, so I have a recording of it. The word and means we're going to set up multiplication every single time. Every single time, multiplication is going to occur. And. So, reading example 3, it says, what is the probability that if a random card is pulled out of a deck of cards, that the card will be a 6 of hearts? Well, if you have any knowledge of a deck of cards, there's only one 6 of hearts in a deck. So you have a 1 in 52 chance. Okay. We read on. It says, let's say the card you pulled wasn't the 6 of hearts, but it was actually the 4 of clubs. Is the probability of pulling a 6 of hearts on the next pull the same? The answer to that question, again, is no. When you do not put the card back in play, okay? And that's the thing. You pulled the 4 clubs out and you leave it out. You now go to a 1 in 51 chance. And what that does is that increases your chances on the next pull of maybe pulling that 6 of hearts out. As you eliminate cards out of the deck, you're increasing your chances of pulling what you're wanting. So yeah, they are dependent of one another, provided the card is not put back in play. Your denominator changes. So we want to talk about mutually exclusive versus overlapping events. Does anyone know what a mutually exclusive event could be? Okay, a mutually exclusive event is two things can't happen at the same time. All right. A good example of this: if you roll a die, you cannot land on a 2 and a 5 at the same time. They are mutually exclusive from one another, and that's it. You can't do it. So, how would it appear in a word problem? So, let's pretend at Topsail High School in the winter, the female athletes can either compete in basketball, indoor track, or cheerleading. Okay. We took a survey. We found out five of the females compete in basketball, 2% compete in indoor track, and 3% compete in cheer. What is the chance that a randomly selected female walking down the halls of Topsail High School, if they were asked, do you play a winter sport, they would do one of those three, okay? So I will tell you this, these are mutually exclusive. You cannot play basketball and cheer at the same time. You cannot run track and play basketball at the same time. You can't be in two places at one time is what we're saying. So the way mutually exclusive events work is you simply add the independent pieces together. So 5 plus 2 plus 3, you have a 10% chance of pulling a female from the hall and say, hey, do you play a winter sport? And she's either gonna say yes or no, right? She's either gonna do basketball, track, or cheer. You have a 1 in 10 chance, you have a 10% chance of pulling someone, a female athlete, and they playing an actual winter sport. So, mutually exclusive events, add the independent events together. That's what I want you to take away from this. Add the events together. There's no multiplication. Add them. Okay? So what does the overlapping look like? Overlapping events. Can you give me an example of an overlapping event? All right. What does overlapping mean? Well, we've talked about overlapping, right? When we talked about the bouquet of flowers, remember that? Right? We had in this bouquet we had roses, daisies, and lilies, and this one we had carnations, tulips, and daisies was the overlapping piece. So we're back to talking about overlap again. And so this I kind of came up with this example, and this really kind of hits home. What are the chances of rolling a single die and it landing on an even number, or the number being a multiple of 3? Well, we need to think about this now. Let's do the individual probability of the even number. Then let's figure out what the probability is of a multiple of 3, right? So I've broken this down for you. So the chances of a die rolling and being an even number, you can only roll a 2, 4, 6, right? That's a 3 out of 6. That's a 1/2. You have a 1/2. You have a 50% chance. The chances of rolling a 3 or 6, 3 and 6 are multiples of 3. That's a 2 and 6. That's a third, right? I left the denominators the same because just like mutually exclusive, we have to add these events together. So 3 out of 6 plus 2 out of 6 is 5 out of 6. There's a slight issue though with overlap, okay? The 6's repeat. And we've talked about this with that Venn diagram. When you have categories, when you have lists that have the same number, you don't write it twice. You can't use it twice. You must subtract it or take away one of the numbers. So I want you to, from the 5/6, subtract the 1/6 chance. The 1 being the 6 is the common 1 piece. So, how did this work? 3 plus 2 is 5. 5 minus 1 is 4, so it's 4/6. 4/6 is a reducible fraction of 2/3. 2/3 is, I think, like 66.7%. So, just out of curiosity, little bonus question here. What is another way I can come up with 1/6 without doing any of this simple breakdown? Okay? What can I do? How can I get, well, I know what you're probably going to say. You're going to say, how can I take these two and get this? Y'all are just going to say, subtract 3/6 minus 2/6 and get 1/6. And I agree with that, but that doesn't work all the time. The answer is, if you multiply the independent events together, all right, we're back to multiplying again. If you multiply them together, that makes 6/36, which is actually a reducible fraction of 1/6. And I'm going to show that to you on a couple of future examples here. All right, so overlapping events, you must subtract the overlap of the independent events. Or means add, and I cannot stress that enough. When you see the word or, you're going to add and subtract the overlap. That's the key. When you see the word and in here, you simply multiply. There is no overlap. There is no overlap with the and. With the or, there's going to be your overlap. Okay? So this, from here out, it might get a little dicey as far as flipping back and forth in screens. What is the probability of either rolling an odd number or a number less than 5 on a standard die? So let's do the first one. What's the chances of rolling an odd number? Odd number, we have a 3/6 chance. Well, the chance of rolling a number less than 5. All right, well, what are the numbers less than 5 on a die? 4, 3, 2, 1, right? That's 4 numbers. That's 4/6. So, let's begin the process, right? When we see the word or means add. So we're going to add these together. And right now we're sitting at 7/6. We can't have 7/6. We can't have more than 100% chance. There's got to be some overlap in there. So you got to think about this. What are the odd numbers on a die less than 5? Well, it's the 1 and the 3, right? So if you do this, 1, 3, 5 are your odd numbers. Your numbers less than 5 are 1, 2, 3, 4. So when you're looking at these two groups, how many numbers overlap? And the answer is 2. The 1s overlap and the 3s overlap. So we must subtract the overlap. And there's 2 of them. There's 2 numbers that overlap. So your answer to this problem is 5/6. And then, just convert it to percent. I'm not going to keep continuing to turn these into a percent because you should not. So the next example, so what I've done is I've used red, blue, green, and purple. Those are my 4 suits. Each card is numbered 1 through 8, all right? So let me see if I can do this for you guys where you can see it. And I'll probably just do it in the middle, what I'm going to do, and then just answer my problems independently. So we have 1, 2, 3, 4, 5, 6, 7, 8. And we got 1, 2, 3, 4, 5, 6, 7, 8. Then I think we have purple and blue. So you can kind of see what I'm doing here. 1, 2, 3, 4, 5, 6, 7, 8. Notice I'm kind of lining them all up. Sorry about this. 1, 2, 3, 4, 5, 6, 7, 8. Okay. I know I've kind of written into this problem here, but forget about that because this is going to get erased when we move to the next one. So, with a visual here, it's going to make this much easier for us. So this P means probability. So this question is reading, what is the probability of pulling a blue card or a card numbered 6? All right. So let's do the first part. How many blue cards are there? There's 8, right? How many cards total do we have is the question. Well, it looks like we have 32. So we have an 8 and 32 here. Okay? What about a card numbered 6? How many cards are numbered 6 here? Well, we got 1, 2, 3, 4. So we got 4 out of 32. So we're going to add those up right off the get-go. Just add them up. 8 plus 4 is 12 over 32. Let's talk about the overlap. Overlap is any cards that are blue numbered 6, right? So the overlap is the combination of these two in one lump, like clump. And the answer to that is, yeah, we do. We have a blue card number 6. We have one of them right here. That's it. One thing I like to do sometimes is circle. Going back to the Venn diagram, another way of doing this is like, here's all your blues, right? There's your 8 out of 32. Here's all your 6s, right? There's your 4 out of 32. Just like on the Venn diagram, if you watch the video, the double circle, the intersection, the overlap, intersection, overlap, the same thing, is what we have to subtract. So we have an overlap here of 1 out of 32. So the answer to this problem is 11 over 32. Okay, so you remember, we got to add and subtract when it is an OR problem. So let me erase these. And I like doing it with the bubbles. I think it's like my version of the Venn diagram is writing it out and circling. Yeah, okay. All right, there we go. Let's do this one. What's the probability of pulling a red card? Well, let's do it. Here's all your red cards, right? There's all your red cards. So you have an 8 out of 32 chance of pulling a red card out of the whole deck. Card greater than 5. All right, so you got a whole bunch of these little buggers. Cards greater than 5 are 6, 7, and 8. All that right there. So how many in that vertical circle are there? There's 3, 6, 9, 12. So right now we're sitting at 20 over 32. Okay, you don't add your denominator pieces. You should know that by now. The question is, let's talk about the overlap. Do we have any numbers that got double circled? And the answer is yes. The 6, 7, and 8 here in red got double circled. And we can't use them twice. We can either use them for one category or the other, but you cannot use them twice. So we got to take them away. So we have a 17 and 32 chance of pulling a red card or a card greater than 5 in this problem. Again, subtract the overlap. Subtract the overlap. So on this next part, I'm going to have to pull up a standard deck of cards, and we're going to answer these questions using the deck of cards that I pull up. So this is going to get a little tricky here doing this one, but I'll do my best to try to demonstrate and illustrate them all. So just bear with me. I know it kind of makes the video a little bit longer than necessary, but you know, you also get good quality examples. So for those of you that don't know what a standard deck of cards looks like, here it is. Right? You have 4 suits. You have your hearts, your diamonds, your clubs, and your spades. Everything is 2 all the way through to an ace. So there's 13 in a suit, okay? 4 suits make 52. So let's go back to the previous question. So the question is, what are the chances of pulling a face card or a heart? Face card, heart. Face card, heart. Okay, so we're doing this one. So I'm going to circle all my face cards. And what are face cards? Face cards are the jacks, queens, and kings. If you ever played cards, you know. These are all my face cards. Okay? So how many of those do we have? We have 3, 6, 9, 12. So we have 12 out of 52. Right? So we have 12 out of 52. And then I think the next part said, or a heart, right? Let me make sure I'm reading this correct. Face card or a heart. Okay. So the hearts are at the top. So we should have 13 of those. So that makes a total of 25 out of 52. Look for overlappage. We have 3 cards that are overlapping. The Jack, Queen, and King of Hearts are overlaps. So we must subtract those from the total. So your answer to the first one is 22 over 52. Which again, just put it in the calculator if you want the percentage, okay? So let's go back. Let's write that one in. So this one was 22 over 52, and I'll write it up here. It was 12 over 52 was your face card. Hearts was 13 over 52. Then we had 3 overlaps. And that makes 22 out of 52. And you don't have to reduce these fractions because at the end of the day, I'm going to ask you for a percentage anyway. You see what I'm saying? So 42.3%. All right, so the next one, we're going to use the same standard deck. I'm going to erase the loops here. It says pull an ace or a club. An ace or a club. So this is probably a little bit more simplistic here because there's not as much working parts. Ace or a club. Oops, let me get that out of here. Come on, ace or club. There, good boy. All right, all your aces. So the probability of pulling an ace or a club, and there's the problem right there. Pulling an ace is going to be 4 out of 32. You have 13 clubs right here. I'm sorry, not 32, but 52. My apologies. And that's 17 out of 52. There is only 1 overlap, so we're going to take that 1 overlap away. So we're looking at 16 over 52 for that answer. Okay? 16 over 52 is my answer to that one. All right? So that's how the deck of cards works. Again, when it says or, plan on doing an overlap. This last one, I kind of like. Yes, I made it up, but it's going to serve the purpose. And I'm actually going to take this back to something we did called segment addition postulate. All right? And it still involves overlap, but it doesn't say or, but it's going to involve overlap. It says in a class of 30, 12 kids are vegetarians and 25 of them read comic books. I want to know how many kids are vegetarian comic book readers. In other words, what in the heck, what am I asking for? What am I asking for? I'm asking for, wait for it, I want to know the overlap number. I want to know the overlap number. And I'm going to relate it back to something I did with segment addition postulate. You may recall we had something that looked like this. Some lips, called them lips, and they were kind of messed up a little bit at times. This area in here is called overlap. So how does this work? Well, we have a total of 30 kids. 12 of them are vegetarians. 25 of them are comic book readers. There's a handful of them that do both. And we need to figure out how do we know how much they do? Or how many of them do both? If you recall, back when we first covered this, you would add the two lips together and subtract the overlap. Just like we've been doing. We've been adding the independent pieces together and subtracting the overlap. So this is the problem we're going to solve here. So that's, that's a 25, excuse me, I'm sorry. So that's 37 minus x equals 30. Right? And you can kind of see how this is going to unfold. Negative x equals negative 37. So, no, not, yeah, that should be 7 though, sorry. So x is 7. So 7 kids are vegetarian comic book readers. Again, we're taking it back to the old school here. Doing some old school segment addition postulate. This was a common question on the Math 2 exam several years ago. How to calculate that overlap, okay? Good stuff, good stuff. Let's see what I have for the next slide here. I'm gonna try to scoot along. So, so this guy here, all right. We had some, I was noticing, and I don't think I included it in one of the previous videos when we were doing the probability section. And the whole dice thing was throwing people off. Now the kids that were in class, most of them saw something that was not shown in the video, and I apologize in the video for not showing it, but I need to talk about it. When we're rolling 2 dice at one time, a lot of people said, well, the denominator is 12. And that is simply not the case, all right? So I want to show you what's really happening when we roll 2 dice. Now we said that when we have compound probability, we're multiplying the independent pieces. So with dice, it's not out of 12, but it's out of 36. And people are like, I don't get it. I don't understand how there's 36 different roll combinations. Well, I built a chart, or I build a chart for you to see how this works. And this is going to take a while, and I apologize for the length of the video, but in order to properly educate you, you got to see all this. Okay? Okay, so what I'm doing, and I could probably do this by hand quicker, so I'm just going to make these lines. So I'm going to make a chart, a table with all of the possible roll combinations. And you're welcome to use this chart so you don't have to draw one out. Okay, so I'm going to do 2 different colors here. 1, 2, 3, 4, 5, 6. That's one color die. The other color die, 1, 2, 3, 4, 5, 6. So I'm going to come here and I'm going to put every number vertically in place. And you can kind of see what I'm doing here, right? 4, 4, 4, 4, 4, 4, 5, 5, 5, 5, 5, 5, 6, 6, 6. And we'll do the same with my numbers here. 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2. 4, 4, 4, 4, 4, 4. And what I'm doing is I'm showing you guys the 36 different roll combinations. Because there's multiple ways of rolling whatever you want. In other words, if I want to roll a 5, there's actually 4 ways I can roll a 5. With a red 1 and a blue 4, or a red 4 and a blue 1. They're completely different. Different dice are making the same thing. So it's really good to have this visual in front of you when we're trying to answer dice questions, especially when there's 2 dice involved. So if I said, what are the chances of rolling a number that adds up to make 3? Well, it's these 2 right here, right? So there's 2 out of 36 total. What are the chances of rolling 2 numbers that add up to make 10, right? So there's this one, and this one, kind of diagonal. You have a 3 in 36 chance of rolling a 10 when playing Monopoly. So, with this visual in place, I can now take you back to the Monopoly game. Okay? So example 1 says, you're sitting on Indiana Avenue. Indiana Avenue sits right here. And you're fearful of going to jail. So if you've ever played Monopoly, right, you don't want to go to jail because you go over here and you stay in jail. What is the probability that you would roll a 7, 1, 2, 3, 4, 5, 6, 7, and you would actually have to go to jail? Well, when we look at our chart, okay, so let's make this blank here. The question is 7. How many ways can we make a 7? And it's this diagonal right here. 1, 2, 3, 4, 5. There's 6 different ways I can roll a 7 on just 2 die. Okay? There's that diagonal right there. Ding, 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 ding. So it's 6 out of 36 is my answer to this problem. Okay, so I'm gonna pull this guy back down. Pull him back up. And so I have a 6 out of 36 chance, which is what, 1/6, which is 16.7%. Okay? So that's how that works. Next question. You're on Pacific Avenue. That's right here. And your buddy owns hotels on these 2. So if you've ever played, these are the most expensive properties on the board, right? If you put hotels on there, you're pretty much going to go bankrupt. Game's over. You need to not land on these 2 places. Well, that's a 1, 2, 3, 4, 5, 6, 7, 8. You do not want to roll a 6 or an 8. So the question is, what are the chances of landing on one of his properties? In other words, what are the chances of rolling a 6 or rolling an 8? Okay? So when we go back to our board here, these are what we call mutually exclusive events, by the way. Because you can't roll a 6 and an 8. So we add them together. So the chances of rolling a 6, so here's all your 6s. Right, that's 1, 2, 3, 4, 5. So rolling a 6 is a 5 out of 36 chance. We said or means what? To add. Rolling an 8. 1, 2, 3, 4, 5. There's 5 ways of rolling an 8. So you have a 10 in 36 chance of landing on one of his properties. Is there any overlap in here? No. It's mutually exclusive, right? You can't roll a 6 and an 8 at the same time. So you have a 10 in 36 chance, which is a little bit under, what, 30% of landing on the dude's property. So just putting that up here, rolling a 6. We said it was 5 out of 36 for rolling a 6. An 8 is also a 5 out of 36. They're mutually exclusive. So 10 over 36, which at the end of the day, pull that down one more time. 10 divided by 36. So you have about a 28% chance of losing the game, 27.8%. Okay? So there it is. That's compound probability. That's all the little bells and whistles that we have to offer for this section. I hope this helped. If you have any further questions, feel free to join me in a Google Meet.